Okay, let's dive right into this. Welcome to today's explainer. We are doing a rapid, highly focused technical overview of a seriously fascinating new system called InfantCrySense. If you have ever wondered how artificial intelligence, specifically convolutional neural networks, and advanced acoustic feature extraction is actually stepping into the nursery to decode human biology, well, you are in exactly the right place. We're going to get right under the hood. So think about this for a second. For generations, interpreting a baby's cry has relied entirely on subjective human judgment, right? A caregiver's experience, how tired they are, even just the background noise in a room, it all introduces massive inconsistency. But what if we could completely remove that subjectivity? That is exactly the problem InfantCrySense is built to solve. It uses a deep learning framework to literally translate raw acoustic signals into actionable, real-time smart healthcare data. Section 1. The audio processing pipeline. Okay, the audio cleanup process fires through 4 distinct steps before the AI even touches it. First, the audio is standardized to a mono channel at exactly 22.05 kilohertz. This is basically the perfect sampling rate to capture vocal frequencies without adding unnecessary computational bloat. Second, we trim the fat, automatically stripping away any dead silence at the edges of the recording. Third up is RMS normalization. You can think of this as standardizing the volume knob, so a cry coming from all the way across the room is scaled identically to one right next to the microphone. And finally, the system chops this continuous audio stream into uniform 3-second segments that the AI can easily digest. Section 2. Extracting the acoustic fingerprint. To actually analyze these clips, the system relies on MFCCs, or Mel Frequency Cepstral Coefficients. Now, without getting completely lost in the weeds here, MFCCs are essentially an acoustic representation that actively mimics how the human ear perceives sound. By extracting exactly 40 of these specific coefficients from our 3-second audio segment, the system generates what is essentially a foundational acoustic fingerprint of the infant's vocalization. But we don't stop there. We actually layer that fingerprint to capture a crucial extra dimension, which is time. Channel 1 holds our base MFCC features, but as we all know, infant cries change pitch and intensity super rapidly. So Channel 2 extracts the delta, the first-order temporal dynamics, which you can think of as the velocity of those acoustic changes. Then Channel 3 extracts the delta-delta, the second-order dynamics. That's essentially the acceleration of the sound. Stacking all of this together creates a dense, highly detailed 3x40 by 130 feature tensor. So we have our math, now it needs a brain. Section 3, CNN and real-time detection. That dense mathematical tensor we just built gets fed straight into this CNN architecture. And notice how the convolutional layers scale up aggressively, going from 32 to 64 to 128 all the way to 256 filters. This scaling is highly intentional. It basically forces the AI to learn increasingly complex, highly discriminative acoustic patterns that are hidden deep inside the cry. Throughout this process, the network keeps itself stabilized with batch normalization and ReLU activation, gets mathematically condensed through pooling layers, and is rigorously fine-tuned during training using the atom optimizer and a cross-entropy loss function. Out in the real world, the system uses overlapping analysis windows to continuously listen to its environment. It feeds those overlapping 3-second segments into the trained CNN, where a softmax function goes to work on the back end. The end result? You get a continuous binary output, cry or not cry, and it's delivered instantly alongside a strict confidence probability score. So what does this all mean for us? The result is a highly scalable, fully automated system that removes caregiver subjectivity completely. And the best part? It does this without attaching a single physical wire or sensor to the infant. It operates continuously and totally non-invasively, laying a massive technical groundwork for the next generation of smart childcare and neonatal hospital wards. It's a real game changer. It really makes you stop and wonder, doesn't it? If a standard microphone and a well-trained neural network can reliably decode the distress signals of a newborn, what exactly comes next? As AI deepens its ability to decode human biology, what other involuntary signals will our smart environment soon learn to interpret? Thank you so much for joining me for this technical explainer. Stay curious, keep learning, and I'll catch you next time.